In this video, we're going to show you how to use the output from the Microlab visual spectrometer in absorbance mode in order to generate an absorption spectrum. So again, the steps are going to be similar to what we did in the emission. We're going to need to have a wavelength calibration, and then we're going to have a blank spectrum, and then a sample spectrum, and we're going to compare in Excel the blank and the sample spectrum in order to generate the absorbance plot. So first of all, we're going to open the file, and again I have saved an image of the blank spectrum. Here we have it. Again, this isn't the greatest. In fact, we only show 6 lines. We don't show the 7th line in the helium spectrum. But we've got, again, the fiber optic cable bringing in the light from the helium emission tube. And then we have in the sample compartment potassium permanganate. Well, actually, this is the DI water blank. We have a stirrer so that when I add the potassium permanganate to it, I can get a new spectrum without changing the position of the vial and without changing any of the settings. So this little funky stuff right in here is actually the stirrer in the slit. This is our deionized water spectrum. It's basically light coming through from the incandescent lamp reflected off a piece of white printer paper through the slit to the eyepiece, and this is the view from the right of the slit. On the left of the slit you'd have the mirror image. So the first thing I'm going to do then is take the rectangular selection tool and go down here. I'm going to select the whole thing so I can get a reproducible pixel count, and then we'll do the analyze and plot profile. And here you have the plot profile with 6 of the 7 lines. Okay. Next thing we're going to do is just use the up arrow to move this rectangle up and select the blank spectrum. This is going to take a little while. I apologize. And again, to save time, I'm just going to go to the bottom. I'm not going to bother going to the top. So we have this. We're going to analyze that part and do the plot profile. And now we have the plot profile, the intensity. Again, out here we basically aren't seeing anything because we don't have any light gathering ability in the ultraviolet. And then we kind of see the absorption profile of everything, the vial, the water, I suppose the grating itself, and the paper. So this is our blank background that we'll be subtracting from our sample. Alright, we have all the information we need from this photograph. Let's go back and open up a photograph of the sample. I have a number of potassium permanganate samples in here. I'm going to pick one. I'm going to take this 42A, open that. Now again, if we compare that to the other one, we can see that it lines up very well indeed, okay, including the calibration file. Okay, so we don't have to worry so much about collecting calibration information. This is all going to be within a nanometer or two, and we're looking at very broad absorption bands. Okay, so again, going in here, we're going to select as best we can the entire image, and we're going to analyze that to get the plot profile. Alright, now let's close these photographs and look at the plot profiles. So here we have the sample, here we have the blank, and here we have the helium from the fiber optic. So we'll be using this information, helium from the fiber optic, to convert pixels into wavelength, and we'll be ratioing the intensity of the sample to the blank in order to get absorbance, and we'll be able to generate a plot of absorbance versus wavelength. So we'll go into an Excel file. Again, this is available from Microlab. Nothing special, but it's something that I wrote, and we're able to again, pick the 6 visible lines from helium and compare those to the actual wavelength so that we can get the calibration plot of wavelength versus pixels. And we'll copy that and we can actually generate the helium intensity plot. And then we'll do the same thing in terms of copying the pixel and intensity for both the background and the sample, and then calculate the absorbance by taking the log of the ratio of the sample to the background. Again, this assumes that you have 0 intensity when you have no light. I'm not sure how good this is, but it, empirically it seems to work out. So let's go and put those numbers in. So the first one is at 584. Second one, 769. Third one, 936. Fourth one, 1001. Fifth one, 60. And the last one out in the red. And up here. There we go. Okay, so here we have a calibration line. Notice again that we have approximately 0.12 pixels, nanometers per pixel. So in other words, about 5 pixels per nanometer, 8 pixels per nanometer. All right, let's go back and copy. We're almost done. Copy and paste the helium. This gets us our helium spectrum. We're going to copy and paste our background. And then we'll copy and paste our sample. And here we have it. Now what I've got over here, again, the wavelength versus absorbance, where absorbance is the log of the ratio of the sample intensity to the background intensity. In addition to the raw plot, here we have the absorption spectrum. Now I have to confess that in addition to the raw plot, I've done some smoothing. Since we have 8 pixels per nanometer, I've done a 15 pixel smooth. So I'm taking the absorbance level over 15 pixels and taking the average. And I'm actually plotting that. So this turns out to be about a rolling average over 2 nanometers, which is fine when you have a very broad absorption band. So there you have it. What we've done is taken the photographs of the DI water and the potassium permanganate sample. We've taken the helium spectrum, light piped in through the fiber optic cable so that we can get a wavelength absorption, and we've used that information to convert pixels to wavelength, and by ratioing the intensities of the sample to the background we can get an absorbance plot. Now this isn't necessarily the best, but I think what it does really nicely is give you a comparison between the visual absorption and the graphical output, and hence it's a great educational tool. It probably won't replace your diode array spectrometer, but actually, when you get right down to it, it almost could.